Hi, it's Professor Adam. Let's talk about acid-base reactions. From Bronsted-Lowry acid-base theory, a reaction between an acid and a base can be considered as a reaction between an acid and a base to form the conjugate base of the acid and the conjugate acid of the base. How can this be used to predict the direction of an acid-base reaction? Hydrochloric acid is a strong acid. One reason for this is because it is assumed to completely ionize as the Ka is much larger than 1. This means that we can assume the initial concentration of the acid is going to be equal to the concentration of the hydronium at equilibrium. This reaction has two conjugate pairs, one between the hydrochloric acid molecule and the chloride ion, and the other between the water and hydronium. Of the two acids here, HCl is stronger than H2O, and for the bases H2O is stronger than chloride, which means that the equilibrium will lie to the right. Unlike hydrochloric acid, which is a strong acid, acetic acid is a weak acid. This is because, when dissolved in water, it is only partially ionized, and the Ka value is much less than 1. This means that the concentration of the hydronium ion is much less than the initial concentration of the acid. The equilibrium has two conjugate pairs, one between the acetic acid molecule and the acetate anion, and the other between the water and hydronium. The equilibrium lies heavily to the left, and for a 0.1 moles per liter acetic acid solution, only about 1% of the acetic acid is ionized. For the weak acid system, the hydronium ion is stronger than the acetic acid molecule, and the acetate ion is stronger base than water, and so the equilibrium will lie to the left, as this produces the system with the weakest acid and base. These reactions illustrate the point that all proton transfer reactions proceed from the stronger acid and base to the weaker acid and base. So for the reaction between acetic acid and bicarbonate, the Ka values indicate that the carbonic acid is a weaker acid than acetic acid, and the Kb values indicate that the acetate is a weaker base than bicarbonate, meaning that the reaction will favor the side to the right with the weaker acid and base. For a standard acid system with a conjugate acid and base, the net reaction can be determined. Looking at both sides, A- exists as both a product and a reactant, as well as HA. This gives an overall reaction which is the same as the autoionization of water. Remembering back to chemical equilibria, the overall Kc value is simply the product of the individual K values, and so we find that the product of the equilibrium constants define the overall Kc expression, which is the same as Ka times Kb and is equal to Kw. This relationship, then, is true for any acid-base pair. Because there are both strong and weak acids and bases, there are four general types of acid-base reaction. A reaction between a strong acid and a strong base, a reaction between a weak acid and a strong base, a reaction between a strong acid and a weak base, and a reaction between a weak acid and a weak base. Reaction between a strong acid and base produces a salt. For the reaction between hydrochloric acid and sodium hydroxide, sodium chloride is produced. Looking at the individual reactions of the acid and base to dissociate, they have this complete ionic reaction, which gives this net reaction. The net reaction for the acid-base reaction of strong acids and bases is always the reaction of the hydronium ion. This reaction is the reverse of the autoionization of water and has a very large K value, which means the reaction will mostly form products. If equal concentrations of acid and base are added together, the solution will be simply salt and water. The reaction between a strong acid and a weak base produces an acidic solution whose pH is determined by the pKa of the acid, if the number of moles of each species is the same. The net ionic equation for the reaction between hydrochloric acid and ammonia is shown. The Kb of ammonia is higher than that for water, and so it is a stronger base. The Ka of the hydronium ion is much larger than for ammonium, making it a stronger acid. This means that if equal concentrations of acid and base are combined, the net result is an acidic solution, because ammonium is also the conjugate acid of a weak base with the pH depending on the Ka of the cation. The reaction between a weak acid and a strong base produces a basic solution whose pH is determined by the pKb of the base if the number of moles of each species is the same. The net ionic equation for the reaction between formic acid and sodium hydroxide is shown. The Kb of hydroxide is much higher than formate, and so it is a stronger base, and the equilibrium will lie to the right. This means that if equal concentrations of weak acid and strong base are combined, the net result is a basic solution because formate is also the conjugate base of a weak acid, with the pH depending on the Ka of the anion. What happens if a weak acid and a strong base react? How can the formation of a basic solution be shown? For the reaction of the strong base sodium hydroxide reacting with the weak acid formic acid, the pH value depends on the base Kb value. First, write out the full ionic equation so that it can be split into the acid and base parts. Then determine the Ka for the acid, for which the Kb value of the conjugate base is given. Do the same for the base part, which ends up being the inverse of the water ionization, Kw. Thus, the value for the hydroxide part is much larger than Ka, and the solution will be basic, an overall K value that indicates the equilibrium on the side of the products. Reactions between a weak acid and base produces a solution which will be either basic or acidic depending on the Ka or B values of the species involved. The reaction between the weak acid acetic acid and the weak base ammonia. For this reaction, the reaction will proceed from left to right because acetic acid is a stronger acid than ammonium and ammonia is a stronger base than acetate. The values for Ka and B are the same, and thus the solution is expected to be neutral if equal concentrations of acid and base are used. But what happens if a weak acid and base react and the values of Ka and Kb are not the same? For the reaction of ammonium reacting with cyanide, the pH value depends on the Ka of the cation and the Kb of the anion. The ammonium is the acid in this reaction, and its Ka value can be obtained from the relationship that Kw is equal to Ka times Kb. The cyanide is the base in this reaction, and its Kb value can be obtained in a similar manner. Since Kb is larger than Ka, if equal moles of acid and base are reacted, the solution will be basic. Let's check comprehension.